According to the National Electrical Code, specifically Section 215.9b4, ground fault protection is indeed required on the breaker for the power factor correction PFC capacitor in the described scenario. This regulation states that when connected to an ungrounded conductor or a delta-connected three-phase system, capacitors exceeding 150 volts to ground and rated more than 125 kV amps should be protected by ground fault protection. In this particular case, the power factor correction capacitor is connected to a three-phase delta system and its capacity exceeds 125 kV amps. Therefore, adherence to ground fault protection becomes mandatory. The primary reason behind this requirement stems from the inherent risk associated with ground faults in delta systems. Delta systems typically lack a direct ground connection, which means there is no inherent path for fault current to return to the source. However, the introduction of a power factor correction capacitor alters this dynamic by providing a return path for fault currents, consequently elevating the potential for ground faults. Ground fault protection plays a crucial role in ensuring personnel safety. By detecting ground faults and promptly disconnecting the circuit, it mitigates the risk of electrical shock to individuals who might come into contact with faulty equipment or wiring. It is also important to consider that even if the feed is a 4-wire service entrance system, because there is no return ground path from the power factor correction capacitor back to the source transformer, it is still considered a delta system. A 1000 amp breaker may be significantly larger than what might be minimally required for a 125 kV amps capacitor under the National Electrical Code. Ground fault protection adds a supplementary layer of safety, protecting equipment and personnel from potential hazards. It is imperative to verify the specific requirements outlined in the National Electrical Code and consult with a qualified electrical engineer or inspector to ensure that the installation meets all applicable safety standards and regulations. This will guarantee the safe and reliable operation of the power factor correction capacitor and the overall electrical system. Let's delve deeper into the technical rationale behind the necessity of ground fault protection for delta-connected power factor correction capacitors. To fully comprehend the importance of this safety measure, we must consider the inherent characteristics of delta systems, the function of power factor correction capacitors, and the potential hazards that can arise in the event of a ground fault. A delta system, in its purest form, is a three-phase electrical system that does not have a direct connection to ground. This absence of a grounded neutral conductor distinguishes it from Y-connected systems, which typically feature a neutral conductor connected to ground at the source. In a delta system, the three phases are connected in a closed loop resembling the Greek letter delta, hence the name. This configuration provides several advantages, including increased reliability and reduced harmonic distortion. However, it also presents unique challenges when it comes to fault protection. One of the primary challenges of delta systems is the lack of a readily available path for fault current to return to the source in the event of a ground fault. In a grounded system, such as a Y-connected system, a ground fault creates a low impedance path for fault current to flow back to the source through the neutral conductor and the grounding system. This high fault current triggers overcurrent protection devices, such as circuit breakers or fuses, to quickly interrupt the circuit and prevent further damage or injury. In contrast, in a delta system, a ground fault may not immediately result in a high fault current because there is no intentional grounding point to facilitate the flow of fault current. Instead, the fault current may circulate through the system, potentially causing damage to equipment and increasing the risk of electrical shock. This is where the introduction of a power factor correction capacitor comes into play. Power factor correction capacitors are used to improve the power factor of electrical systems. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the electrical power is being wasted due to reactive loads such as motors and transformers. Power factor correction capacitors work by providing reactive power to offset the reactive power consumed by these loads, thereby improving the overall power factor of the system. When a power factor correction capacitor is connected to a delta system, it can inadvertently create a path for fault current to return to the source in the event of a ground fault. This is because the capacitor acts as a low impedance path for current to flow between the phases of the delta system and ground. If a ground fault occurs on one of the phases, the capacitor can allow fault current to flow from the faulted phase to ground and back to the source through the other phases. This fault current may not be high enough to trigger conventional overcurrent protection devices such as circuit breakers or fuses because it is distributed among the phases. However, it can still be sufficient to cause damage to equipment and pose a safety hazard. This is why ground fault protection is required for delta-connected power factor correction capacitors exceeding a certain size. Ground fault protection devices are designed to detect even small amounts of fault current flowing to ground and quickly interrupt the circuit before damage or injury can occur. There are several types of ground fault protection devices available, including ground fault circuit interrupters (GFCIs) and ground fault relays. Ground fault circuit interrupters are typically used in residential and commercial applications to protect individuals from electrical shock. They are designed to detect ground faults as low as 5 mA and interrupt the circuit within a fraction of a second. Ground fault relays are typically used in industrial and commercial applications to protect equipment from damage due to ground faults. They are designed to detect ground faults as low as 30 mA and can be adjusted to trip at different current levels and time delays. When selecting a ground fault protection device for a delta-connected power factor correction capacitor, it is important to choose a device that is specifically designed for this application and that meets the requirements of the National Electrical Code. The ground fault protection device should be installed in accordance with the manufacturer's instructions and should be tested regularly to ensure that it is functioning properly. In addition to ground fault protection, there are other safety measures that should be taken when installing and maintaining delta-connected power factor correction capacitors. These include properly grounding the capacitor enclosure, using insulated conductors and connectors, and providing adequate clearance around the capacitor for ventilation and maintenance. It is also important to train personnel on the proper procedures for working with power factor correction capacitors and to provide them with the necessary personal protective equipment (PPE) such as gloves, safety glasses, and insulated tools. By taking these safety measures, it is possible to minimize the risk of electrical shock and equipment damage when working with delta-connected power factor correction capacitors. It is essential to prioritize safety and to adhere to all applicable codes and regulations to ensure the safe and reliable operation of electrical systems. To further elaborate on the topic, let's discuss some additional considerations related to ground fault protection for delta-connected power factor correction capacitors. Firstly, the size and type of the power factor correction capacitor play a significant role in determining the need for ground fault protection. As previously mentioned, the National Electrical Code mandates ground fault protection for capacitors exceeding 125 kVA when connected to an ungrounded conductor or delta-connected three-phase system. However, even for capacitors smaller than 125 kVA, ground fault protection may still be advisable in certain situations. For instance, if the capacitor is installed in a location where there is a high risk of ground faults, such as a wet or damp environment, ground fault protection can provide an extra layer of safety. Similarly, if the capacitor is used to correct the power factor of a critical load, such as a hospital or data center, ground fault protection can help to ensure the continuous operation of the load in the event of a ground fault. Secondly, the location of the ground fault protection device is also an important consideration. Ideally, the ground fault protection device should be installed as close as possible to the power factor correction capacitor to minimize the amount of unprotected wiring. This will help to reduce the risk of damage to the wiring and equipment in the event of a ground fault. In some cases, it may be necessary to install multiple ground fault protection devices to provide adequate protection for the entire system. For example, if the power factor correction capacitor is connected to a lawn feeder, it may be necessary to install a ground fault protection device at both the source and the load ends of the feeder. Thirdly, a coordination of ground fault protection devices with other overcurrent protection devices in the system is crucial. Ground fault protection devices should be coordinated with other overcurrent protection devices, such as circuit breakers and fuses, to ensure that the ground fault protection device trips before the overcurrent protection devices in the event of a ground fault. This will help to minimize the amount of disruption to the system and prevent damage to equipment. Coordination studies should be conducted to determine the appropriate settings for the ground fault protection devices and the overcurrent protection devices. These studies should take into account the characteristics of the power system, the loads being served, and the potential fault currents. Fourthly, regular testing and maintenance of ground fault protection devices are essential to ensure that they are functioning properly. Ground fault protection devices should be tested at least annually to verify that they are tripping within the specified time and current limits. The testing should be performed by qualified personnel using calibrated test equipment. In addition to testing, ground fault protection devices should also be visually inspected on a regular basis to check for any signs of damage or deterioration. Any damaged or deteriorated components should be replaced immediately. Fifthly, proper documentation of ground fault protection systems is crucial for troubleshooting and maintenance. Detailed documentation of the ground fault protection system should be maintained, including wiring diagrams, settings, and test results. This documentation should be readily available to qualified personnel for troubleshooting and maintenance purposes. The documentation should also be updated whenever changes are made to the system. Sixthly, training of personnel on the proper operation and maintenance of ground fault protection systems is essential. Personnel who are responsible for operating and maintaining electrical systems should be trained on the proper operation and maintenance of ground fault protection systems. This training should include instruction on the principles of ground fault protection, the types of ground fault protection devices, the testing and maintenance procedures, and the troubleshooting techniques. The training should be conducted by qualified instructors and should be updated on a regular basis to reflect changes in technology and regulations. Seventhly, compliance with applicable codes and standards is mandatory. Ground fault protection systems must comply with all applicable codes and standards, including the National Electrical Code, NEC, and other relevant industry standards. These codes and standards provide detailed requirements for the design, installation, testing, and maintenance of ground fault protection systems. It is important to consult with qualified electrical engineers and inspectors to ensure that the ground fault protection system meets all applicable requirements. Eighthly, the use of arc flash hazard analysis can enhance safety. Arc flash hazard analysis is a process of evaluating the potential arc flash hazards in an electrical system and determining the appropriate safety measures to mitigate those hazards. Arc flash hazard analysis can help to identify areas where ground fault protection can be used to reduce the risk of arc flash incidents. The analysis should be performed by qualified personnel using specialized software and equipment. Ninthly, consider the implications of harmonics in the system. Harmonics are distortions in the electrical waveform that can be caused by nonlinear loads, such as electronic devices and adjustable speed drives. Harmonics can interfere with the operation of ground fault protection devices and can cause them to trip unnecessarily. It is important to consider the presence of harmonics when selecting and setting ground fault protection devices. Harmonic filters may be required to reduce the levels of harmonics in the system. Finally, remember that safety is paramount. Ground fault protection is an essential safety measure for delta-connected power factor correction capacitors. By following the recommendations outlined above, it is possible to minimize the risk of electrical shock and equipment damage and to ensure the safe and reliable operation of electrical systems. Always prioritize safety and consult with qualified professionals to ensure that all applicable codes and standards are met. Additional considerations include understanding the specific application and load characteristics. The type of load being served by the power factor correction capacitor can influence the selection and settings of the ground fault protection device. For example, if the load is highly sensitive to voltage sags or interruptions, the ground fault protection device may need to be set to trip more quickly to minimize the impact of a ground fault. In such cases, careful coordination with other protection devices is crucial to avoid nuisance tripping. Furthermore, the grounding scheme of the overall electrical system should be taken into account. While the power factor correction capacitor may be connected to a delta system, the rest of the electrical system may be grounded in a different manner. The interaction between the delta system and the grounded system can affect the performance of the ground fault protection device. It is important to ensure that the ground fault protection device is compatible with the overall grounding scheme of the system. Another important aspect is the maintenance and testing of the ground fault protection system. Regular maintenance and testing are essential to ensure that the ground fault protection device is functioning properly and will trip when required. The testing should be performed by qualified personnel using appropriate test equipment. The test results should be documented and compared to previous test results to identify any trends or deviations. Any problems or discrepancies should be investigated and corrected promptly. Moreover, it is important to consider the environmental conditions in which the power factor correction capacitor and the ground fault protection device are installed. Harsh environmental conditions, such as high temperatures, humidity, or corrosive atmospheres, can degrade the performance of the equipment and reduce its lifespan. It may be necessary to provide additional protection, such as enclosures or coatings, to protect the equipment from the environment. It is also important to ensure that the equipment is properly ventilated to prevent overheating. Furthermore, it is crucial to keep up to date with the latest codes, standards, and industry best practices related to ground fault protection. The electrical industry is constantly evolving and new technologies and techniques are being developed. By staying informed about the latest developments, you can ensure that your ground fault protection system is up to date and provides the best possible protection. This may involve attending industry conferences, reading technical publications, and participating in training courses. In addition to the technical aspects of ground fault protection, it is also important to consider the human factors. Ground fault protection systems are designed to protect people from electrical shock, so it is essential to ensure that personnel are properly trained and aware of the hazards of electricity. Personnel should be trained on how to identify and respond to ground faults, and they should be provided with appropriate personal protective equipment (PPE). They should also be instructed on the importance of following safety procedures and working safely around electrical equipment. Finally, it is important to remember that ground fault protection is just one component of a comprehensive electrical safety program. A comprehensive electrical safety program should include elements such as hazard identification, risk assessment, safe work practices, training, and auditing. By implementing a comprehensive electrical safety program, you can create a safer working environment and reduce the risk of electrical accidents. The appropriate level of ground fault protection is not solely determined by code compliance, it's about ensuring the safety and reliability of the entire electrical system. A thorough engineering review, considering all the factors discussed, is essential to making informed decisions. It's a multifaceted decision, but one that prioritizes safety and equipment protection above all else.